Second, there was a handout. Oh, that's going to be a neat beginning to this. I think that should be all right. I think maybe that'll work. Anybody that wasn't here last time needs that handout from last time? That thankfully I have some copies.
Can I just have another one?
Well, we'll see. Anybody else? So yes. You will?
Thank you.
Sure. Now, obviously, it's always my hope that you're actually doing the homework. There's a purpose to it so that you get practice. Doing this practice quiz and checking out the answers is one thing, but doing the homework will ensure that you really get the concept. The questions on the actual quiz won't necessarily be exactly the same format as these. They'll have the same concepts, but not necessarily the same setup. So doing the homework will ensure that you will have seen all the different setup possibilities. Hint, hint. Yeah?
I have a question from 444.
Okay.
Number 4.
Oh, cool. All right. So here's the thing. I think we did this one last time. If 11%, and I think it said 17%, but actually the research I could find, it still said 11% of left-handers in the world. So I think last time we did, remember we did, it was like 17%. Let's pretend like that's what it is. If I want to pick 3 people, and you're sitting there saying, how does this relate to my question? I'll get it. If I want to pick 3 people, what's the probability that the first one's left-handed and the next 2 are right-handed? So the first one's got to be left-handed, so that would be 0.17. And
The remainder of the
0.83. And now, why did I have to worry about changing the probabilities? Because the second you pick somebody, you're kind of assuming you're not going to pick the same person again, right? 3 different people. So why didn't I have to worry about how that might change?
Replacement?
No, it's not with replacement. What was true about the population that we're dealing with? This was of the world, remember? Which is nearing 7 billion. I don't know. Maybe it is at 7 billion. I can't keep track. So here's the bottom line, and I think I said this last time. If the sample you're picking is less than 5% of the total population, then you can treat them as independent, right? So we looked at specific example, picking 2 cards without replacing. Remember how this worked? And you want the probability, let's say that I get 2, no, let's say this. I get a 7 and then an ace.
7052?
Careful. How many 7s?
4.
4 of them. So I got 4 chances out of 52 to get a 7. And you can throw that one away.
4 out of 51.
There's still 4 aces, right? Out of 51 cards now because you threw one away. So I've got to worry about what the next one does based on what the first one was, right? I've got to worry about it there. Why? Because 2 cards out of 52, that might be enough. That might be enough to make me have to do it. Plus, it's easy to do. I can keep track of that, right? I can keep track of that as it moves along. But when I'm talking about 7 billion people, I really don't want to have to set up 17% of 7 billion to put that number over 7 billion times 1 less over 1 less times, oh my God, right? So thank God we got this 5% rule that will help me. If it is less than 5% of your population, you are allowed to treat it as if it's independent, like the second guy doesn't change, right? Yeah.
Why is that 51 and not 50 if you get 2 cards that you do?
At this stage, how many cards have I picked? At this point, how many cards have I picked?
0.
So So probably get a 7. So here's the probability that I get a 7. Throw it away. I'm about to go pick my next card. I haven't done it yet. 7, 8 cards have I picked? 1. Cool. Yeah. Yes, son.
Can you go over 16 on 4.4.3 and 157?
16. Real quick, I just want to make sure I answer the question. Number 4 says, can the events described in exercise 3 be treated as independent? Well, how many are they taking? In number 3, they say they take 1,068. And how big of a population is it? 477,938. If you divide that, if it's less than 5%, yes. If it's not, no. That's the 5% guideline, right? And what is 1,068 divided by that? Big number, I like it. 1 out of 500 is like 0.2%, 0.002? Ah, I got to show my math skills off sometimes. That's all I got. I can't dunk a ball. I got to divide quickly in my head. All right, so that is definitely, that's about 0.2%, less than 5%. So then can you treat them as if they're independent? Yes, because it's less than 5% of the whole population. Exactly, 0.002, which is 0.2%. Yeah, change it to a percentage. Yeah. That's what that one is all about. So when you have a large population, you can basically just treat it as independent. Thank God, because remember what we did when I had like 8 people? And I wanted the first one to be left-handed and everybody else to be right-handed. What's the shortcut then? 8, 3 to the... How many more people?
7.
Yeah. And I couldn't do that if I couldn't treat them as independent, because I'd have to figure out exactly what each percentage is now. Based on, I picked somebody, now what is it? I picked somebody, now what is it? Screw that. Let me treat it as independent, and then I can just slam them all together, right? That's going to help out a lot in chapter 5. Okay. So where are we at? Sorry, Sonia. Which one was it? 4.3?
4.3. 16.
16? Sobriety checkpoint, all right. Dutchess County Sheriff Department. He saw that 676 drivers were screened and 6 were arrested for driving while intoxicated. Oh, okay. Oh, man, they really build this up for something really kind of silly. So this is 16 and 4.3. What's the probability of intoxicated? Yeah, where'd they come up with that?
6 out of the 676.
Yeah, because they found 6 people. Well, wait, where'd it go? 6 out of the 676. So if you do that, you should get that. Yeah. Does that match up? Cool. Right? Now look how silly this is. I think I put this up here a couple times, but everybody remember what that symbol there means? That bar over that? Not. So the probably intoxicated is 0.00888. What's probably not intoxicated? What's it gotta be?
1 minus.
Yeah, 1 minus that.
99.2.
99112. You guys with me? That's it. That's all there's to it. Yeah. And that exactly relates to that probability of at least one discussion that we had, because the probability of the opposite of something is 1 minus the probability of that something. Always. And at least one is the opposite of none. So that's nothing new. It's the same idea. Is that cool? Okay. Yeah.
I have a silly question, sorry. If you say something simple or ask us something simple like 79% of women have red hair, what percentage doesn't have? If we say 0.21 or 21%, is it going to make a difference?
No. As long as you don't say 0.21%.
Okay.
So a lot of people do that. They'll put the point and they'll put the percentage symbol, one or the other. right? Now I understand sometimes it will be like 0.2%. But when you get 0.21 as an answer, don't just put a percent symbol on there. Either give me decimal or give me percent. That's the only thing to be careful about there.
Yeah.
But 0.21 is the same thing mathematically as 21%. Yeah. 22, right?
Yeah.
See the instructions and table on the preceding page. Ooh, they're so nice. So they give you a little chart on the page beforehand, right? So let's see, if M is the event of selecting a challenge made by a man, what would M not be? Yeah. So if the probability, if they're asking for the probability of not man making a challenge, and you don't have to go through all the whole process of figuring out the probability of man and 1 minus, why not just figure out what not man is? And we're going to assume here that it's woman, right? So now you just have to look up the probability of woman.
Or challenge not made.
Well, this is all about people that have actually made challenges, yeah. So everybody in this study made a challenge, and it's all about was it successful or not. And you see what they're kind of getting at with this study? Do you see what this study might kind of lean towards? Why would they break it down men and women that made challenges, and then they say how many challenges were successful and how many weren't? What might they be studying to look for?
You're trying to show that in men's sports, the challenges get, I don't know how to say it, but.
If they treat men and women differently,
Yeah.
right? Bottom line, this kind of study happens all the time. And very often it studies differences between racial, how races are treated differently with police or with applications or whatever. But here's one about gender. How are men and women treated differently? In this case, it's about something that's not quite so controversial as pay or something like that, or being hired. Tim?
I have a question from the practice quiz, number 4. So you can kind of just like common sense wise just know those are dependent because you can be a male and own a Toyota.
Oh, I see.
So you figure first the probability of being a male, then the probability of a male given that they own a Toyota. So that's the correct math.
You can't do the first part of your question, though. You can't reason it out.
Male and.
Because just because you could be a man and own a Toyota, that actually says it might be independent. It doesn't say yes or no. Okay? The funny thing is, and I didn't want to get too deep into this, but if I have two things that are mutually exclusive, they are totally dependent. And the reason is, if I blindfold myself, if the room is full of cats and dogs, there's no cat dogs, right? And somebody blindfolds me and I go around and hopefully don't step on anybody. I pick up an animal. What's the probability it's a cat? Let's say equal cats and dogs. 10 cats, 10 dogs. It's probably I'm holding a dog. 50%. I take my blindfold off. Given that it's a cat, hey, it's a cat. What's the probability that it's a dog now?
0.
0. It's a freaking cat. So it's almost too easy. People get all confused. If they are mutually exclusive, there's no way that you can be both. So it's impossible for it to be independent then. Because the probability of one thing happening, if that happens, it kills the other guy's chances of happening. So why are kings and clubs independent? Why could they be independent? Let me say it like that. Because there are some kings that are clubs. Right? Well, what about clubs and hearts? Those are totally dependent. Given that it's a club, what's probably the heart now? 0%. See, it's killed its chances. Okay, cool. So that's kind of related to that. Which I forgot the original question, but hopefully that had something to do with it. But yeah, no, number 4, you've got to show. You've got to show the math. You've got to show me the probability of the thing by itself and the probability of the given. And show me that they're either equal or not equal. There's really no way around it. You can't, everybody always tries to explain it to me. No, that can't work. You've got to show me the math. Yeah.
So for 4-4, number 18, when you have to do without replacement for B, because the probability based on the chart there,
Yep.
it would be first 2 out of 100, and then it goes down to 1 out of
Let me catch up. Let me see. So they're taking 3 around, so I can find that probably that they're all in group B and RH negative.
It's 2.
Oh, good. So there's only 2. I love it.
then it would be